Good afternoon. I'm Dan Freed, Director of the Harvard Center of Mathematical Sciences and Applications. It's a pleasure to welcome you to this second webinar with the First Proof people. Let me say that in the chat, you're going to find a lot of links that will tell you about what we do here at CMSA, our engagement across mathematics and science. And I particularly recommend the YouTube channel for lots of interesting lectures and sessions that have happened, including the webinar we had last week that described the First Proof project. But for today, there's going to be an announcement of the results from the second batch. So let's begin by introducing everybody on the panel. So we'll start with the First Proof editorial board. Mohammed.
I'm Mohammed Abu Zaid. I'm professor of mathematics at Stanford University, and I'm executive director of First Proof.
Rachel.
I'm Rachel Ward, professor of mathematics at UT Austin, and I'm on the editorial board of First Proof.
Lauren.
I'm Lauren Williams. I'm a professor of math at Harvard, and I'm also on the editorial board.
Nikhil.
I'm Nikhil Srivastav. I'm a professor of math at UC Berkeley and a senior scientist at the Simons Institute. And I'm also on the editorial board.
And we also have joining us today two mathematicians who contributed problems to this round. Jonathan.
Hi, I'm Jonathan Mattingly. I'm a professor of mathematics and statistical science at Duke University.
Larry.
I'm Larry Guth. I'm a professor of math at MIT.
Okay, so I'll turn it over to Mohammed.
Okay, thank you, Dan, both for hosting this webinar and also for hosting us at CMSA last week. So this is the announcement for the results for the second batch of First Proof. The first batch was a very informal process, and the results I'm gonna describe were a result of a much more formal process, which I'll say a few words about. But by the end of this webinar, there'll be a paper posted, which includes quite a bit more detail. So I will now start by sharing my screen. So we were funded by multiple institutions. I just want to acknowledge them. In addition to CMSA, there was also the Simons Institute at Berkeley. The ICARM is going to help us with some online discussion fora. And then there were three funders, Survival and Fellowship Fund, the AI for Math Fund, and then two companies, Anthropic and OpenAI, who gave us donations which were with no strings attached, and which we used to support the people who wrote the problems as well as the referees, which I'll get to that later. So the problems, like last time, what we did is we went around and solicited 10 questions. These are questions whose solutions or problems whose solutions do not appear on the internet anywhere. We try to pick them from diverse areas of mathematics. We often ask people things of the form, well, if you have a result that's going to be appearing soon and you're willing to extract from it some small part, maybe something whose proof is up to 8 pages long, would you be willing to share it with us and write it in a format that makes it possible to use in this benchmark? So these are the first 5 problems that we have. And today we will hear from Larry Guth and Jonathan Mattingly, and they will tell us about their problems later. This is the second half of the problems we have. And later we'll have a discussion of just very brief, visuals about how the AI systems that we tested performed on each of these questions. But one thing that I do want to highlight is that it's not just finding the problem. We assembled these problem writers for 2 days. Some of them were in person, some of them were on Zoom, and we tried to really kind of craft questions that were at the right level, that involved some kind of testing, making sure that there wasn't some result in the literature that would make the results easier than the problem writer expected. And also we asked them to write very detailed solutions, which you will be able to find again on our website once this presentation is over. Okay, so this is a slide that's here mostly for the mathematicians in the audience who are not experts in AI systems. So when I we'll move on and start talking about the submissions, which is like the systems that we tested. The word harness will appear. And this word harness is some technical term. What it refers to essentially is something like a program, something that you can write yourself or have an AI system write it for you. And what it does, there's a technical definition that appears on the slide, but roughly speaking, what it does is that it puts an LLM or maybe multiple LLMs, multiple large language models, inside the system where they can talk to each other and take multiple actions depending on the outcome of various processes. So it can, for a mathematician, the idea is you start with a problem that we're asking, is the square root of 2 irrational? And you would like a final output, which is a proof. Okay? And in between, there will be multiple agents. And in the simplest possible model, there's going to be 2 of them. There's going to be one that tries to prove that the square root of 2 is irrational, and another one is going to verify whether this proof is correct or not. And then you need to design some kind of feedback loop where maybe the verifier finds a mistake and sends it back to the prover, and then the prover tries to fix the mistake, and it goes around for a while. That's somehow the person designing it has to figure out how to make this work and make this not descend into an infinite loop. And essentially every system we'll be describing today was built, as a harness of this nature. Now, in this setting, you often talk about what base model you use. So the prover and the verifier, they are often some kind of LLM. And that LLM can be, provided by OpenAI or DeepMind or Anthropic or any other company that builds AI systems, including things which are open source. But that's not what we're discussing here. All the systems we ended up testing rely on a commercial model as its base. So the submissions, the systems we tested, there were 4 of them. One of them, we called them A, B, C, and D at the beginning of this process for us to not be biased and to not be like, oh, that's this person or that person. So we tried to keep this as unbiased as possible. So 3 of them were by commercial group, academic groups. One is IM Proofbench. They're members of multiple academic institutions, but Johannes Schmidt, who's the lead, is based at ETH. The other group is focused on UCLA, and there's a long list of contributors here, some of which are mathematicians and some of whom are computer scientists. The third system we tested is the publicly available version of GPT 5.5 Pro. When you test a model like this, you have to decide what prompt are you going to use. And we asked Mehtab Sani and Sebastian Bubeck, who are at OpenAI, to provide us with a prompt. And they kindly provided us with one, and it's listed in our, it'll be listed in our report. And that's the results basically reflect what that prompt gave. And finally, there is a group at Princeton led by Sanjeev Arora that also submitted a harness for testing. Now, the way this worked is that except for OpenAI's system, which is just something publicly available, you can just call it, every single one of these groups provided us with, a directory, like a repository that included some amount of code. And then we brought it onto our servers. We had an API key, which is basically a way of communicating with the large language models that these harnesses rely on. We ran it. There was a constraint that we told everybody at the beginning, which is there's going to be a time constraint of 24 hours. There are other constraints which can be specified in more detail, but this is in some sense very restrictive one. And at the same time that the models are allowed to call any large language model as long as it's something that the general public has access to. Okay? So the different harnesses had different designs, different LLMs that they called, but that's the common feature of all of them. Okay? So now probably the thing that people care the most about here. So this slide kind of shows the results of our testing. So the editors who are Nikhil, Rachel, Lauren, and me. So we met last week with 30 expert mathematicians that are specialists, so 3 specialists in each of the 10 questions that I showed at the beginning. We asked them to independently read the submissions. So and then start writing reports. But at some point after they started writing the report, we allowed them to talk to each other, because sometimes mathematicians get stuck. Like, I don't understand what this, what this solution is saying. Can we discuss and make sure that there's no error? But all the writing was then done separately. After the writing was over, we reviewed all of it and made a decision. And we decided to, and we at the beginning had told all the submitters that we would classify all the results into either an immediate rejection. That would basically mean, like, there doesn't seem to be something from this submission that looks like it could lead to a solution. What we call a major rejection, which is a request for major revisions, which is like, this strategy could possibly work, but there are large gaps in it. And I would not be confident that it's correct, that it can be corrected, until I can see a second version or a third version and see that these issues that I'm flagging can actually be fixed. A minor revision, which is what's shown in yellow here, and that basically indicates that there is some flaw, but I'm confident that a competent mathematician could fix it, and I don't need to look at it again. Okay? And the last part, which was just about the mathematics, where we just say, like, the mathematics is, there's no error here. And that's what's shown in green. Now, one thing that we do want to highlight, and will come up later, is that the distinction between minor and major was kind of a delicate issue for our referees. Very often they would say, like, based on the criteria you told us, this is a minor thing, but for an actual journal submission, I couldn't imagine this being published, usually because of issues of how it's written or citations, or sometimes, you could even call it plagiarism, because the large language models do not write like humans do. What I would say, the way that I would read this slide is that for 3 of the problems, 4, 8, and 10, the models didn't really make any significant progress. But for the rest of them, which is 7 of them, the models were either able to produce a flawless solution, or so close to being correct that mathematicians would look at it and say, well, any experts in the field can just, if I were to point at, like, this line is not quite right, they would be able to fix it. So that's the outcome. So we have a more detailed and maybe slightly overwhelming slide here, which shows the result of every single review, a summary of the result of every single review. So what I want to highlight is that the number of reviews is either 2 or 3. So that's why there are either 2 boxes in each of these, in each of these regions, or 3 of them. So as before, black means that the reviewer suggested that we should just immediately reject this. Major meant that the reviewer said there's really a major issue here. And on this slide, I decided to separate the 2 kind of minor issues that most often occurred. So there is a minor math, which is kind of yellow and red, and that's the situation where the referee really identified some mathematical issue that they felt like had to be fixed. And there is the one which is the other one, yellow and green, where the referee kind of said there doesn't seem to be any mathematical issue of note here. However, there are problems of citations that would make this solution not be something that could be reasonably publishable. The other thing that I want to say, if you look at this slide and you're trying to compare the comparisons of the different group, is that if you remember from before, C was basically 5.5 Pro. So B is built entirely on GPT 5.5 Pro. The base system for D is Gemini 3.1, which is less of a specialized model for mathematics. And I will say something about A on the next slide, so that's why I'm not saying anything about it right now. The last thing to note is that there is a gap here for problem 6. So this was a technical, for submission A, this was a technical problem. It's not because submission A kind of decided not to turn in a solution. It was because there was a call to, they made a call, technically like a call to OpenAI servers, and despite repeated attempts, could never manage to get any response, and there was no human in the loop. This is something that we encountered in our own testing. When we tried to get a result from OpenAI for problem 6, we made 2 attempts and kind of the system timed out, but eventually Rachel actually, who was doing this, figured out a technical way of extracting a solution from OpenAI. And we suspect that if a human had been involved in the loop, there would not have been a gap in here, and just a small change in parameters could have fixed this issue. Okay, so the last slide that I want to present gives a more detailed comparison of the performance of Submission A with GPT 5.5 Pro. So the first thing that I want to say is that Submission A kind of mostly relied on 5.5 Pro for its large language models. However, it had within it a certain component which also allowed it to call to other models by Gemini or by Anthropic. I should have said Anthropic. And this part of the system was not always turned on. I looked at the numbers and looked about half the time it turned on. But the main thing that I think one can get by looking at the slide is that if you look at the results, they kind of speak for themselves in the sense that you can see that there are more correct results on the left side than there are on the right side. But another thing to highlight, and I think this is something we said quite a bit about in our discussion when we designed this, is that we would like to have some amount of transparency about the cost and the technological cost that goes into producing these answers. And for GPT 5.5 Pro, they're listed on the right. I do want to say most people access this using some kind of subscription. This is not what we did. This was a cost for each one of these questions. We sent OpenAI a question, and then we got a response, and we got a bill. And for question one, the bill was $13, and so on and so forth. The costs for Submission A, as you can see, are substantially larger. So that is something that presumably is a consequence of trying to get better answers. And at the same time, you can also notice that all the calls from GPT 5.5 Pro are limited to be basically 1 hour. We didn't see in this testing any situation where the answer took longer than an hour to be produced, whereas the limit for Submission A is basically this 24-hour limit that we put in at the beginning. I mean, you see this, 22 hours and 55 minutes. That's basically because they wanted to give themselves some kind of cushion to make sure that they wouldn't time out. So the comparison is here. If you want to look at comparisons for the other submissions, we basically have all this data, the cost, the time, even more detailed information about the number of input tokens and output tokens and so on and so forth. And all of that will be listed on the paper that we will release, presumably during this talk. So that is all I have to say about very general context. And I think now we should move on and discuss some mathematics.
Rachel, are you introducing first speaker?
Do you just want me to go, Rachel? Is that the plan?
Go ahead.
Okay. Yeah, okay. Sorry, I wasn't sure. So hi, I'm Jonathan Mattingly, as was already said. Let me get my screen up. Of course, the minute. All right, for some reason it's not coming. Here we go, sorry. All right, so all right, so can everyone see that, I hope? Yes? All right, so let me tell you a little bit about this question. So this question came together, I should say, when I was at a program at SL Math last fall, and Oleg Bukowski and Lorenzo Zambati were also there. And Lorenzo and Oleg have been thinking about this question. So it's a question about a stochastic partial differential equation. So it's on the line 0, 1 with Dirichlet boundary conditions that say 0 at each end. And I've written the equation right here. I assume you can see my cursor, hopefully. Here's the equation. And it's a heat equation. So the first term is just derivative in time, then second derivative in space. And then the last term is a space-time white noise. So just at every moment, every time, you can think infinitesimally of every point being agitated independently by a small Gaussian random variable. And then there's this term, which is this delta function. So whenever the field crosses 0, there's an kick, a delta function kick. Of course, this is just a distribution, not an actual function at each moment. So that causes a lot of technical difficulties. And Lorenzo and then Oleg have spent a fair bit of time over a long amount of time making sense of this equation, studying its properties, understanding it. But one question that really hadn't been understood was it's pretty straightforward. A reasonable exercise for a mathematician in the field, just to show that we know what the invariant measure of this problem is. That is to say, we know what the steady state of this problem is. It's a certain Brownian bridge, but we didn't know that it was the only steady state. So we didn't know that there was a unique invariant measure, that there was unique ergodicity. And so that was the question we asked. Prove or disprove that there's one and only one invariant measure for this system. Actually, what we asked was to prove that there was at most one invariant measure. We didn't ask to demonstrate that there was an invariant measure. All right, so we had a proof which used something called asymptotic coupling. Oops, what happened there? Did it go away for you? It went away for me. Let me try to fix that. Don't know why. Okay, is this back? Yeah?
Back.
Give me a thumbs up. Great, thank you. So we introduced a drift, and this drift, through a change of measure, drove these two equations starting from different initial conditions to each other asymptotically at infinity. And if for any two initial conditions, they're driven together asymptotically with kind of a push that leaves the measures still absolutely continuous with respect to the original measure, then that's enough to prove unique ergodicity. A simple exercise with Birkhoff's ergodic theorem. Now, the AI, so I guess 3 of the AIs produced essentially just a recap of different methods of proving this and left large gaps that were equivalent to the thing that we all knew was the problem. So we didn't really have anything to learn. The scaffolding A actually produced a correct proof. So it proved a correct proof. And what's interesting, actually, so the proof that we turned in to show everyone was, I said, an asymptotic coupling proof. But before that, we actually started another proof. And our intention had been to go back to that proof, in fact, to finish it, but we hadn't. And that proof brought together some ideas that I had developed and some ideas that Lorenzo and Oleg had developed. And we were still teaching each other to fit them together. And our first attempt to fit them together, and one of them is a stochastic sewing lemma, and another one is kind of a shifted Gersonov's method. Sorry if for the non-experts, maybe Rachel or Mohammed, you can chime in and ask me questions presumptively to tell me, or Lauren to tell me to be more explicative. But we tried that, and our first pass failed. The way that I presented this kind of shifted Gersonov didn't match well with the kind of estimates that Oleg and Lorenzo had out of the box, their toolkit. And what was interesting is that the AI used a related representation, this time-shifted Gersonov type thing, and that it fit directly into the kind of estimates that one got right out of the box for the stochastic sewing. Now, what's interesting is that actually the representation I picked was something that came partial. I mean, I don't know. I haven't looked at the transcript carefully, but it's something that's in one of my papers used in a different way. So it's something that I knew, but I hadn't realized that it was the right way to present it to the people who were experts in this stochastic sewing. Now, I don't know if with time we would have figured it out, but the AI did. And so it did produce a correct proof. I will say that it then took this fact that it quickly proved using this, and then wrapped it in a whole bunch of extra stuff. It talked about reversibility. It talked about spectral gaps. It talked about lots of things that were actually not necessary. It actually had the proof right there. And then it went on for a couple more pages. It did eventually reason and state a correct theorem and give the proof at the end, but it proved the correct technical gap that was needed, and then it kind of went around a few times the block before it got back to the point. And so, I said unnecessary extras, but they're all correct, and they were used correctly. But it could have just stopped with about 3 more lines after it had proved the main technical lemma. But that's not what it did. Let's see. Is that anything else you want me to say? That's kind of the main thing I wanted to say.
Yeah, that's great.
Yeah.
Thank you.
So next, Larry Guth, who's the Claude Shannon Professor of Mathematics at MIT, is going to be telling us about the problem that he contributed.
Okay, great. Let me see if I can share.
And in the meantime, let me remind everybody to please use the Q&A if you have questions.
All right. Does that look good? Okay. So the problem that I shared is from an area called quantitative topology, which is a mix between quantitative geometric estimates, that's stuff like the isoparametric inequality, with topology. And the geometric input in what we'll talk about is something called k-dilation, which measures how a mapping stretches k-dimensional volumes. So, well, okay. So I'm going to explain this idea, this notion. Suppose you have a mapping from Rn to Rn, and you want to think about how the mapping is kind of stretching the domain. One thing you might look at is the norm of the derivative. The norm of the derivative controls how the mapping stretches lengths. So if you have like a curve in the domain and you want to understand how much longer or shorter the image of the curve will be compared to the original curve, you would look at the norm of the derivative. Another classical thing you would look at is the determinant of the derivative. The determinant of the derivative describes how the mapping F distorts volumes, meaning n-dimensional volumes in n-dimensional space. So those are both classical, but a little more recently, people have started to think seriously about in-between dimensions. So lengths are one-dimensional, n-dimensional volumes are n-dimensional, and you could pick a dimension k anywhere in the middle. And the k-dilation of F describes how the mapping stretches the k-dimensional volumes. So if I say the k-dilation of a map F is at most 1, it means you take any k-dimensional surface in the domain, and then the volume of the image is at most the volume of the original surface. The k-dimensional volume of the image is at most the k-dimensional volume of the original surface. Okay, does that make sense? All right. So in quantitative topology, we're going to try to relate something quantitative and geometric with topology. And Gromov suggested and explored the question, how is the k-dilation of a mapping F related to the topology of the mapping F? And here is a sample theorem from his work from the 1970s. So suppose you have a map from the unit 3 sphere to the unit 2 sphere. And topologically, the interesting invariant is the Hopf invariant. And Gromov proved that the Hopf invariant of the map is at most a constant times the 2 dilation squared. And this is the right estimate at sharp up to a constant factor. Okay, so that's a sample of this field of quantitative topology trying to connect something topological with something quantitative about the geometry. And I was working in this field as a PhD student, and I had a first problem, and I was completely stuck on my first problem. And so I decided to take a break and to try to prove something simpler. And I picked out something that I thought seemed totally obvious to try to prove. And this was the something. So suppose you have two rectangles, n-dimensional rectangular boxes called R and S. And then my problem was study the minimal possible k-dilation of a diffeomorphism or a degree 1 map from R to S. And I have like a rectangular box R, and I'm going to try to sort of stretch it somehow into a rectangular box S. And I want to stretch the k-dimensional volumes as little as possible. And it seemed like I thought it should be obvious that the minimum would be given by a linear map, that you should just stretch everything in a uniform linear way and that there would be no advantage to doing some kind of weird bending. So I tried to prove that as a simpler thing, but it turned out that was false. And that became my thesis problem to understand how this really works. The minimum is not linear. So what is it? And that was what I worked on for my thesis. All right. So let's give it a name. Two R and S are n-dimensional rectangles, and the k-dilation from R to S is the smallest k-dilation of any degree 1 map from R to S. So, okay, by the way, this says R comma boundary of R goes to S comma boundary of S. So it means the boundary of R has to be mapped to the boundary of S. That would be true if you had a diffeomorphism, and you need to have some rule like that in order to have a notion of degree. Okay, so this infimum is not coming from a linear map. It's not even approximately coming from a linear map. And in my thesis, I figured out what it was for the sort of easiest non-trivial k's, which is when k is codimension 1, turns out to be the easiest. So for example, for 2 dilation between 3-dimensional rectangles. That was my thesis. And then later, when I was a postdoc, I kept studying this. I wanted to do all the k's and n's. And as a postdoc, I did the case k equals 2, n equals 4. And I wrote it, but I didn't quite finish the paper. So the paper was never published. It's not on the internet. And the full paper is about 20 pages long. And there's an answer, there's a formula for this, and the formula is very complicated. And I sort of gave up at that point about getting all the k's and all the n's. All right, so I had this paper that was never published, so I thought it was a good source of something for this project. The full paper is 20 pages, so that's longer than the framework of first proof. So I took a lemma from that paper. There were 3 lemmas in the paper that are like somewhat not standard. I just picked one of the 3 lemmas, and it has a proof that's more like 5 pages. So that's the problem that I gave. All right, so here's the setup for the problem. Is you have 2 4-dimensional rectangles. And we write down their side lengths, and we have a degree 1 map between them. And the goal is to prove some particular lower bound on the 2 dilation of, so it should be the 2 dilation of this map. It should say the 2 dilation of f. Okay, I'm not going to write down the formula. So the actual formula for the smallest 2 dilation between R and S is like a paragraph long. And so I'm not going to put it on the slide. And the lemma is just sort of a piece of that formula. All right. So in the next little part, I sort of broke the proof into a few ideas that I will attempt to describe in a few words each. All right. So the first idea is to take pre-images of rectangles. So inside of S is a 4-dimensional rectangle, and inside of it, it has like 2-dimensional sub-rectangles that are parallel to the coordinate axes. And the first idea is to study the pre-images of those rectangles. This is basically a standard idea in the area. These are 2-dimensional surfaces. F takes F inverse of sigma to sigma. And so the 2 dilation of F relates the area of sigma and the area of F inverse of sigma. Okay. 2 out of 4 submissions mentioned this idea. Okay. The next idea is to use minimal surfaces. So you can find a minimal surface in the domain whose boundary is this pre-image from idea 1. And the isoparametric inequality, which is something that's in the literature, can be used to control this minimal surface, to say something about its volume. And that in turn gives more information about the pre-image of the rectangle. And so you find out more about it than you would find just directly by looking at the 2 dilation, comparing the more than idea 1. Okay, so this idea 2 is a non-trivial variation on a method from the literature. One of the 4 submissions gave this idea, and it gives a bound for the original problem. The bound is not as strong as the bound that the problem asked for, but it's a non-trivial partial result. It's non-trivial partial progress. Maybe I'll try to say what I mean by a non-trivial variation on a method from the literature. So there's another paper that's in the literature that the model looked at, where you start with a rectangle in the domain, you push it forward to the target, and then you look at the minimal surface that fills in over here in the target. So this is somewhat similar, but we've turned it around. Now we started with a rectangle in the target, we pulled it back to the domain, and we looked at a minimal surface in the domain that fills it. Okay. So it's a genuinely different variation. It's not like incredibly radically different. Okay. So idea 3 is to connect with some more complicated topology. So we have a map from R to S, which is the given map F. And sort of by definition, it maps the pre-image of sigma over to sigma. Sigma are these rectangles in the target, which were from idea 1. Okay. And then we can compose it with a new map that takes the rectangle S to the 2-sphere, and it takes this sigma to star. And if you put them together, it can be topologically non-trivial in a way that's a little more interesting than the degree. This composition can have a non-trivial Hopf invariant. And then if you go back to the beginning of the talk, that Gromov had a method from the 70s to relate the 2 dilation and the Hopf invariant, and you can apply it to this composition. And it gives you some more geometric information, some more information about sigma and the preimage of sigma than we had from idea 1 or idea 2. And that gives the bound that was, the bound that was asked for. Okay, and no submission did this. Okay, so maybe at the end, I sort of said, but I'm just going to summarize the 4 submissions to finish this little presentation, and then maybe see if there are questions. So there are 4 submissions. 2 of them were just nonsense. They just cited theorems or wrote down things that were false, cited theorems that didn't exist, or wrote down things that are false. The other 2 submissions were different in a way that may perhaps have been helpful. I don't know. The other 2 submissions began in their harness by locating and downloading papers from the literature that they thought might be relevant, and then writing sort of an internal summary of those papers. Okay, out of those, the 3rd submission, I would say it sort of found a few standard tools and described them. It had idea 1 and it had kind of part of idea 2. And it didn't answer the original question at all. And instead what it did is it stated and proved a kind of weird result that followed from the tools that it had and had some like sort of superficial resemblance to the theorem. The 4th submission was the best. It had idea 1 and idea 2, and it used them to prove like a legitimate partial result about the question that we asked it. So probably the most fun and interesting thing that can happen is if the AI does something that's different from the human solution. Basically, that didn't happen here, but the 3rd and 4th submissions did mention another thing that they both wanted to try. This other approach didn't go anywhere. They didn't do anything with it, and it doesn't, I'm not sure whether it goes, I don't see how it goes anywhere. And this other thing they mentioned, it was not exactly standard, although it's not all that different from what's in the literature. Okay, so that's my summary of how it went. And I guess if there are, see if people have any questions.
Which problem number was this?
It's problem number 4.
And in terms of the scoring, this is one that was not solved at all. I forgot.
Yeah.
Right. Yes.
Right.
Larry's, there was no solution which was deemed to be correct for this.
Well, or even major revisions. All the editorial decisions were rejected on this problem.
Right. So yeah. So it was slight. It was. We had to think about what category to put it in, because I think the scoring system was predicated on a document that claimed to solve the actual problem. And then you could say, to what extent did it solve the actual problem? But actually, we had 2 documents that didn't claim to solve the actual problem and just to do something that's relevant. And then we had to clarify it. We had to decide how to score them. But in the spirit of the original scoring system, we asked, what level of revision would be necessary to solve the original problem. And from that point of view, they didn't have an approach that with some revision would solve the problem. So they classified it as rejected.
So maybe a couple of quick mathematical questions. One, in Gromov's inequality, there's a square, I think, of the 2-dimensional dilation, but the Hopf invariant appears to the first power. Is there a intuition about the scaling there?
The scaling is, yeah. So one way to look at it is if you have a map from S3 to S2, and then you compose it with a map from S2 to itself of degree D, the Hopf invariant will scale by d squared.
Okay.
And that scaling kind of matches what's happening with the two dilation.
Very good. And Kurt McMullen wants to know if you could say a word about the map G that you constructed, but which the AI systems did not.
Yeah, so this is not a difficult map to construct. This space is not very different from S3 cross S1. And if you forget the S1, we're looking at a map from S3 to S2. It also has some geometry. I think if you decide you want to construct a map here with the given two dilation and which has a given Hopf invariant, it's not very difficult. You cut the domain into cubes and you do something simple on each cube. But I guess what I thought was somewhat novel is to decide to compose with a map over here afterwards and to then look at the composition and the Hopf invariant of the composition.
Okay.
So maybe we can move to some questions about the results of the experiment generally.
Sure.
Yeah, should I stop sharing and pass it on to?
Sure, yeah.
Okay.
So, Mohammed, do you want to share your slides again? Any questions or comments about process for producing the results or the results themselves?
Well, let me ask each of you, I guess to the extent that this second batch and first proof generally is a snapshot in time about where the AI systems are in terms of doing research level mathematics, what's your conclusion from this very fresh experiment? Nikhil, you can start.
I mean, well, what we saw is that out of these 10 problems, 7 of the problems received a grade of minor revisions or above from at least one system. So it's we can say that, you know, for this level of problems, these AI systems can solve many of the problems. And the nice thing is that we have kind of a clear picture of the process. So we're posting the logs, prompts, all that stuff online. At the same time, they didn't solve all the problems. Yeah, it'll be interesting. I mean, it's very difficult to try to explain why they had particular outcomes on these problems. But there are a few patterns that we noted that we note in the report. But I would say the you know, the point of these experiments maybe is to keep doing them at regular intervals so we can see at different points in time how this is changing. And we plan to do another round in like August through September.
So has any of you noticed a pattern in which areas of mathematics or even types of mathematical questions the AI is stronger at or has a particular weakness?
So one thing that we can say is that problems that were structurally similar to problems that appeared in the literature tended to have a much higher chance of being solved by the AI systems. So for example, problem 2, which was proposed by Rick Schwartz, was somehow a kind of a translation of a problem that he had solved and published several years ago. And so multiple AI submissions very effectively kind of mimicked that proof, his previous proof, but translated it into this new setting. So that was something that we saw multiple times. Another pattern that we saw that was a little bit surprising was that even though all of the harnesses and also the prompt to ChatGPT Pro, even though all of these harnesses and queries specifically asked the model to provide careful citations, there were sort of there were a lot of gaps in terms of the kinds of citations that you would expect in terms of attributions. So for example, again with problem 2, which was successfully solved by 3 systems, several of these solutions followed the Rick Schwartz previous proof down to even a line by line kind of a level of detail. In some cases, they like borrowed the terminology. They even used the same like specific notation, like BTDNH, but didn't actually even cite his paper at all. So it was quite interesting to see that Harness is very carefully asked to provide complete citations, and yet somehow it seemed that the results produced didn't generally do so.
Okay. And the first point that you made about, it does better if there's something similar in the literature, that's across different fields of mathematics? Or you've seen it
Yes.
in some different
Yes.
places?
We saw that in multiple fields. Like we also saw this for problem 1, which was a problem in mathematical logic.
Okay. So Peter Falb asks how he would assess the difficulties of these problems. Maybe that's a good question for Jonathan and Larry, who supplied the problems. Are these the most difficult problems you might have thought to give to first proof? Or how do you assess them?
Larry, you want to go?
Yeah, so the request from first proof was a lemma with a 5 to 8 page proof from an unpublished paper that was not sort of standard. The proof is not standard. And yeah, I think that's what it was. I mean, I didn't have a huge list of unpublished papers with lemmas that were not standard.
So in my case, I would say, it was something worth publishing. It was something that people were interested in, but it was not something that I was the top of my deck of things I've done this year, exciting things. I mean, it was something where we brought together some people who were interested in it. It was only 8 pages. That was all we were allowed to do. So that's kind of a short proof, unusually short proof in my field. And it was a little bit of a transfer of technology from some, hey, we tried all the things we know how to do. Do you know a way to solve this problem? And then, I had some other ideas, and they had the estimates because it was their problem. And so we worked together to try to connect. And in fact, we were writing it up. We were planning to finish it. We were planning to go back to try to make sure we couldn't do something exactly like what the AI did. So I think it's certainly a good paper. It's certainly publishable, but it's not like, it's not doing something off the chart, if that's what you're asking. This is.
Okay, I think that gives a good idea. So let me ask the 4 first proof editors. Steve Bradlow asked the question, which is now scrolled off my screen, but is there a difference? Did you notice a difference, or did the graders notice a difference of whatever sort in grading human, refereeing human arguments versus the AI arguments?
Yeah, many people said that the way the AI arguments were written had this feature that there was a lot of detail in routine parts and maybe less detail in some of the difficult parts. And so a lot of people said the notation was weird. So you could tell the texture was different. It was written differently from a human submission.
In terms of level of detail, there were a few sort of amusing details included, like I think in one solution, there was a line that said, because n minus d in parentheses minus c equals n minus d minus c, blah, 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 blah. So so it was sort of amusing sometimes to see the level of detail provided for the more or less easy parts.
Okay.
There are a few questions asking about how the difficulty compares to the first round. One way of answering it is that the process used to produce the problems was the same as the first round, which is we kind of just solicited questions from mathematicians, asking them for things that naturally occurred in their research. But the only difference was the page limit was 8 instead of 5 pages. So it was the same process for creating the problems.
I would add to that we included in our process for selection some use of large language models to make sure that the questions we were asking didn't happen to have a solution that was much easier than we expected because there happened to be a reference that proved a lemma that the author was not aware of. And with the development of the technology, and as these things ingest more and more mathematics, and they're trained on more and more of mathematical literature, they're able to catch more of that. So I think just purely based on that, you would also expect that the level was just a little bit harder. But the fundamental thing is what Nikhil said, is that the length was, we allowed for longer human solutions. And this remains the fundamental issue that we run into. In many fields of mathematics, it seems difficult to extract a self-contained statement whose proof is like 8 pages long and that you feel like you want to highlight. But on the other hand, the fact that we are looking for human reviewers to read this in a very short amount of time makes it difficult to expand this much longer. For the third batch, we'll probably be doing a little bit longer than 8 pages.
Okay. Lukman Wahidudin asks which one of the problems that was solved of the 7 had the most surprising or interesting solution. And looking at all of the 7, were most of them translations from the literature, the kind of thing Lauren was saying, building on things in the literature, or were there any that were more innovative?
I mean, there were 3 submissions where referees noted that there were new proofs found by the AI. So to complement, what Lauren said, I mean, there were genuinely new proofs found in this process. It's hard to rank which was the most interesting, but Jonathan's problem 5, there was only one system which produced a correct proof, and everything else got a straight up reject.
And its combination that it came up with was interesting, right? I mean, it was not, it was that we hadn't connected that bridge completely yet. The ideas were sitting on either side, but when it putting on, that's a good idea. That's a nice way to do this, right?
I could say that problem 9, which was an algebraic combinatorics problem posed by Sylvie Cortiel and John Lentfer, asked for a combinatorial interpretation of a certain coefficient, and so I believe multiple AI systems came up with what was deemed a correct answer by giving different combinatorial interpretations than the one that the humans came up with. Now, some referees pointed out that in some of these cases, these new combinatorial interpretations were a little bit strange, like maybe somehow a little bit less natural than the human constructed combinatorial interpretation. But of course, this is something that's a little bit subjective. But this was something that the referees noticed. The AI systems gave novel combinatorial interpretations of a certain class of numbers, but were judged by humans to be a little bit less natural than the one that the humans came up with.
Okay. So maybe in the last 5 minutes, let's look forward to, I suppose you'll call it, third batch. Mohammed already mentioned that the length of the proof might be allowed to grow a little bit. But what did you learn from the second batch that you'll apply in formulating, in crafting the third batch? And what plans do you have for the third batch that you want to share?
Maybe the first thing that I want to say, actually related both to third batch and to one of the questions in the chat, is that there was a question of there was a lot of talk about GPT 5.5 and not much talk about other models. So the situation is that, in fact, we discussed with both Anthropic and DeepMind the possibility of testing some of their models. But essentially, we had some criteria, which is by May 28th, we would need to have something which is publicly available for us to test, because we are interested in things which are open and transparent and not in testing internal models. And at the time, neither company had something which they were interested in having us test, so that didn't happen. One of our hopes for the next batch is that we will indeed have more than GPT 5.5 to talk about. So that's the first thing. I think the second thing that I want to say is that the main thing that we have learned, and it's not I would say reinforced for us. We expected that this would happen, is how hard it is to check these solutions. So, some of them are very easy to, you just look at, the experts look at them and say like, there must be something wrong with the strategy. I just have to go and find what's wrong. And others, like, you start reading, and very often it happens that if you knew that it was one of your colleagues or an expert in the field, that you think clearly they should be able to implement this correctly, but then when you go through and you look at the details, you have to be more careful than usual, and then you tend to find things which would not have occurred in a human solution. So the amount of effort required to check these AI solutions is really quite substantial. And that is one of the things we have to keep in mind as we design things, a balance between allowing things to be longer and harder and making sure that humans can still check them. So that's directly for the third batch. That's probably the main tension we have to deal with.
I see. Anyone want to add something?
Yes, I just want to add that we do also have a community round coming up June 17th, where we will have a second set of a few problems that are released to the community, given more than 24 hours for the community to experiment with solving those. And then there will be a Zulip channel for discussion of the community round problems.
So these are not the problems from second batch, nor the ones for third batch. These are separate
Yes.
problems. So that's June 17th. And how many problems, or what's the plan for that?
There will be a number of problems that is more than 2 and at most 6.
Okay. That gives us tight bounds. Great. Well, any final comments about the second batch or the plans going forward? What was learned? What, at a high level, you're trying to do to learn going forward?
One comment that I just wanted to make quickly is the issue of citations. For problem 3 on batch 2, there was a missing citation where if it hadn't been missed, if it had been connected to the AI solution, then it would have found that there had been more progress that they could have reported, and the AI solution would have been a better, more complete solution. So citations is more than just an attribution thing, but it also, will help these systems become better at providing more complete proofs.
Okay.
I think we'd like to add that a tremendous amount of work of many people went into producing batch 2. We had our 10 problem writers for batch 2. We have more problem writers for the community round. We had 30 professional mathematicians who spent all day last Thursday and Friday grading. And we've been supported by the CMSA and by the Simons Institute at Berkeley. And so just wanted to give a tremendous thanks to all of these individuals and institutions that supported us.
Good. And certainly the mathematical community appreciates the work that all of you are doing and helping us to assess where we are in terms of this new world of AI. So let me thank again the 6 of you for coming today and sharing these results. And let me remind everybody to check out the First Proof website. I think the report will be there. Mohammed, I don't know if you're posting your slides or if those are covered in the report, but everyone can find out more there, and also the community round. And I encourage you to check out the activities at CMSA. In particular, we have 2 weekly seminars starting in September again during the academic year about math and AI. So you might want to check those out. So thanks again for attending.
Thank you.
Thanks, Dan.
Thanks, everyone.